It's really nice to do the method of isocline is if we have a special kind of function where we have no t's in the equation. There's no t's there. So my original function that I showed you didn't have a t. Remember, I had dy dt equals 0.2, sorry, it was df f minus 10. That was my first equation that I showed you. There's no t's here, and these are called autonomous. That's just the name. When there's no t's explicitly written, I mean, there's a derivative with respect to t, but there's no actual t's. And note that if I have any of these, I just have a function of y equals a constant. And so then all my isoclines are lines, horizontal lines. Because why? Because it doesn't change with respect to t. So let me go ahead and just give you an example. Let's say y prime equals y. Let's actually even make it y squared. So my isoclines will be y squared equals some constant. But look, I just end up squaring this, square rooting it, plus or minus c. So y equals plus or minus c gives us the same isocline. Notice that my slope is always going to be positive because I have that y squared there. So if I was drawing these isoclines, the t doesn't change, and so it's just y equals some constant. So this y equals, let's say c is 1, so plus or minus 1. That function looks like, if I draw these lines, y equaling 1 looks like this, and y equaling -1 equals this. And then my isocline, because my c was 1, so both of these have +1. But notice these are just horizontal lines. Let me do another example. Let's pick 4. So a slope of 4. So y equals plus or minus the square root of 4. I am choosing nice numbers, or plus or minus 2. So plus or minus 2 here, oops, I was going to draw, this should be green, and -2. But what was my slope? It's 4, +4. So it's pretty darn steep. And this one's also +4. Okay, so hopefully that gives you an idea of why autonomous ones are nice, that will have these nice horizontal lines, and we just need to find its derivative at that point. Okay?